Good morning. I'll be your warm-up act for today. My name is Richard Fuchs. I've been with Siprec for close to 15 years now. I'm the main guy who keeps breaking RTPengine, and I'm here to talk about some of the new bugs that we have. Quick show of hands, because I'm curious. Who is familiar with RTPengine? Okay, so quite a few, but also a few holdouts. So I'll start with a quick overview of what it is and why it exists. And it exists because we needed a media proxy to solve problems with NAT. Because this was over 10 years ago. ICE wasn't a thing yet. IPv6 wasn't a thing yet. Still isn't really a thing. And there were some other solutions around at the time to solve the problem of RTP behind NAT. But they all had some issues. In particular, the amount of media manipulations you could do was limited. We wanted to do more. But the biggest problem was the performance. The performance was just not good enough. You could handle a few hundreds of calls, and then the CPU would be maxed out. So in order to understand why this happens, and this was not because the software was written badly. So you can optimize this as much as you want, but you will always run into some kind of bottleneck there. So to understand why this happens, we need to get our hands a little bit dirty. This is basically what happens in a media proxy. The packet comes in from the network, goes through the driver, goes through the network stack, is eventually assigned to a socket. The process then picks up the packet from the socket, essentially does nothing with it, might not even look at it, just picks up a different socket, sends it back out there, goes back out through the network stack and eventually out on the wire. From a code point of view, and I promise this is as nerdy as it gets, so I'll try to work quickly here. This is from a code point of view, anybody who's ever worked with the low-level socket interface will be familiar with this. You may have heard of user space and kernel space. There's actually a third context involved here that's usually called interrupt context. This is basically kernel code that executes without being associated to a process, so kind of on its own. And this is where the initial reception of the packet happens. This is the driver runs, the network stack. This is where the packet eventually gets added to a read queue for the socket. And then any process that is waiting for activity on that socket is woken up. Now, execution doesn't immediately transfer to the process. That happens later on. The process needs to be waited to be scheduled in. It can happen on a different CPU even. Typically, the process would be sleeping at that point. Like in a poll or something, it would wake up, it would see, okay, there's activity on this socket, and then it would read from the socket. At this point, execution transfers to the kernel. The CPU needs to do a context switch. Execution then continues in the kernel, where it retrieves the packet, copies the packet out, context switch back to the process where it now has the packet, picks up a different socket, does the send to that socket, which is another context switch back into the kernel, where it then copies the contents out again and adds it to a write queue on the socket. Now the important part here is the context switch. Superficially, this looks just like a function call. But a context switch means the CPU has to take its internal state, save it somewhere, load in a different state from somewhere else, switch to a different privilege level, Then the kernel needs to set up an execution environment, a stack, a page table. It's a whole ordeal. So the context switch itself is the expensive operation here, and we're talking in the order of thousands of CPU cycles, just overhead, just for the context switch. And this is ultimately where the problem lies. So you have at least 4 context switches per packet, and if you have just for one regular VoIP call, that's 400 context switches per second. And if you do the math, 400 times whatever number of calls you have, times how many thousands of CPU cycles it takes just for the context switch. We have math guy here, maybe he can do the math. You'll start to understand where the CPU usage comes from. The current situation, I mentioned we started doing this like over 10 years ago. Current situation is a lot better. Modern CPUs are generally faster. They are much better at doing these context switches. You also have a lot more cores to work with because this helps. This is purely CPU load. You have a dedicated syscall instruction now. Like back in the day, you would have to, this was on 32-bit CPUs. You would have to do an interrupt, which was even worse. On the downside, there's all these fun CPU bugs that were discovered. Meltdown Spectre. There's a new one now, Red Bleed. And the mitigations that the kernel has to do to work around these bugs sit exactly in the system call interface. So the more system calls you do, the worse it gets. And apparently the Red Bleed mitigation, it's pretty bad in terms of performance impact. There's also no special interfaces that the kernel provides to help here with UDP, because we're talking UDP only. For certain specific use cases, there's like send file or splice, but for UDP, there's just nothing. And so there's no way around this. You have to do this send and receive dance for UDP packets. Unless you manage to avoid them altogether, which is what we did. So we taught the network stack to handle the forwarding part. This avoids the system calls altogether. The packets never actually get to the socket. The process never gets to see the packets. It's basically bored when it does that. Now the process still handles the logic part of it, the signaling and the negotiation part. And then there's a control channel from the process to the kernel, where the process tells the kernel what it should do with the packets that are coming in. Not per packet, obviously, because that would defeat the purpose, but it's like a set of rules. This is what it looks like. It's implemented as an IP tables module. If you're familiar with the IP table syntax, it basically sits in the firewall chain, like IP chains, IP tables, or X tables, as it's called now. The way it works, packet comes in, it's handed to the kernel module. First thing it does, it looks at the destination address and port. If it does not know about it, it will return an accept verdict. An accept in the IP table system means continue processing it. And eventually the packet will then be assigned to the socket, and the process will get to see it. If it does know about the destination, it will first make a copy. Now this is technically not necessary, but for us, making the copy, it makes certain things easier. It's a little bit of overhead, but it's not too bad. It will make a copy, it will send the copy out, and it will return a drop verdict. And drop to IP tables means discard the original packet, and then the process never gets to see it. Looking at the signaling part, you have your A and B here talking to each other, or E and B in this case. We implement the offer-answer model. In the most primitive use case, we're just replacing the IP address and the port with our own, so we can do the media proxying. We don't, in the most primitive use case, we don't interfere with the offer-answer model at all. Everything else is just pass-through. All this happens without any knowledge of SIP. So RTPengine doesn't do any SIP, it doesn't like SIP, doesn't want SIP. So it only operates on SDP and RTP. If you look at the control protocol, there are some fields in there that look like SIP, like call ID, from tag, but those are just identifiers. As long as they're unique, it doesn't matter what they are. Control protocols, we have a number of them, UDP, TCP, even HTTP and WebSocket now. The native protocol is kind of a binary protocol, but you can use JSON now too. The next thing we wanted to do is we wanted to talk to the WebRTC world. And in order to do this, we had to implement a number of features like SRTP, ICE, RTC multiplexing. And in order to support this, we had to kind of break the offer-answer model. Now, I'd like to think this is break as in breaking up, not break, but we can talk about this. So now we can interfere in the offer-answer model, and we can have a set of features on one side, like SRTP encryption, but not on the other side. And you can selectively turn these features on and off. So it's not just all or nothing. It's not just plain RTP or WebRTC, but you can have any kind of combination. The next thing we wanted to do is transcoding. So we added transcoding. You can have different codecs running on either side. From Opus, we have AMR support. That's very popular these days. EVS is coming soon, but that's not open source, so we don't talk about this. As for the kernel module, the important part here is that as soon as you do transcoding, you lose support for the kernel module. It doesn't do transcoding. What the kernel module does support is all the SRTP. You can encrypt, decrypt, you can recrypt, all in the kernel module. All the ciphers are supported there. There's a limited number of media blocking features you can do, but in general, as soon as you start getting into the audio stream itself, the kernel module is out of the picture. To recap, this is a quick example of the kernel module's view of what's going on. It's basically a list of rules like this. It starts with a local IP address and port that it knows about, and then it's a set of rules about what to do with the packets. It knows about payload types, so you can selectively forward some codecs, but not others. In this example, there's SRTP decryption there with the keys in there, and then there's an output section that tells the module where to forward the packets to. Then the next thing we wanted to do is Siprec and conferencing. This is where it gets interesting. These two things were brought to our attention at roughly the same time. So for SIP recording, you need to fork the media to a second destination. The offer-answer model in Siprec happens separately, but RTPengine needs to be involved here. Signaling happens with SDP, so that's good because that's what we do. And then for conferencing, we were looking at the SFU use case. Again, you need to fork media to another destination, maybe multiple destination. Signaling still happens with SDP. So we kind of looked at these and thought, well, these are kind of the same thing. If we implement this right, we can support both of them with the same mechanism. As for existing solutions, for Siprec, there isn't really a choice because it's RTPengine handling the media, so it needs to be RTPengine doing the media forking. For conferencing, there's a number of SFU solutions out there. Janus, for example, that's one of the many things that it does. We actually used to use it. It's the video room plugin, that's an SFU. But we thought, well, if we can implement this in RTPengine, because we kind of have to if we want to support Siprec anyway, and we get all the existing features for free, especially the kernel module, then we could eliminate one component from our systems and use this instead. So in order to do this, we had to break offer answer again, and we had to move away from the one-to-one media forwarding that was part of the core design of RTPengine from day one. It's always been one entity talking to another entity. So we had to get rid of this. There was a pretty big change to make. And we moved to a subscription-based model. So we logically split up the media flows into their respective directions, one in and one out for each media party. And then each side of the call, A and B, is subscribed to the other one. So you have one stream coming in, and the other one is subscribed to that stream and receives it. The important part here is, of course, that you can have multiple subscriptions and multiple subscribers for each call party. The design goal in this change that we made is that we needed to get rid of the one-to-one mapping completely, only have one-to-n media mapping in the whole code base, and that this change should be internal only. So for the existing offer-answer model, it should be transparent. To the outside world, there should not be any noticeable difference. And for all the calls that are set up through offer-answer, you would have one-to-n media forwarding, but n would just be one. We also wanted to retain all the existing features, SRTP, transcoding, and especially the kernel module also needs to support this new one-to-n media mapping. And then to support the new features, Siprec, SFU, we had to implement additional methods other than offer answer to support media mapping with n greater than 1. So for the Siprec use case, let's start with this one. This is what a regular call now looks like internally. You have A and B talking to each other. Each one is subscribed to the other one. And now this guy wants to listen in. So we'll simply add a subscription for this guy to one of the call parties, and now it's able to receive a copy of that media stream. And this is not limited to Siprec. You can use this for legal intercept or any kind of media forking scenario that you want. And you can, of course, have multiple subscription. You can have, this is what you do with Siprec. You receive a copy of every media stream, and you achieve this simply by adding more subscriptions. And for the actual Siprec use case, you would have a user agent that is talking to an external entity through SIP, sets up a session there, and this user agent would be talking the control protocol to RTPengine to set up the subscriptions and so on. And this is what OpenSIPs has implemented now as part of their Siprec module. So this exists already. To support this, we added a couple of new methods, subscribe request and subscribe answer. Subscribe request produces a send-only offer SDP from RTPengine. And for Siprec, for example, this is what you would send out in an invite. You are able to do any sort of SDP manipulations that we support. You can add or remove encryption. You can add or remove transcoding. You can do it to a WebRTC endpoint or the other way around. And you can do this for multiple subscriptions at the same time. And then from the external system, you would get an answer STP back that needs to be fed back into RTPengine. This is the subscribe answer. This would be a receive-only STP stream now. This can possibly, if you want to, use different codecs than the original streams. And ultimately this sets up the actual media forking and the flow of media. And then of course there's an unsubscribe as well. From the kernel module, very simple, this is what it looks like. Packet comes in, it makes a copy once for each output stream, and the original packet is then eventually dropped. Just a quick note now here that some people think that is the copying of the data, that is the overhead that actually produces the CPU usage. We find that this is not really the case. It's really the context switch that is the problem, because we've been making copies of packets even in the most simple case, and we're still quite happy with the performance that we get. To support the conferencing case now, we added another new method. This is not a published method. This performs an offer-answer exchange directly against RTPengine. So you publish your offer STP, you get a response back from RTPengine. The published streams you do, those are send only. You can offer multiple codecs. RTPengine would accept one codec only, and you can influence which one it is. So you can give it a list of preferences, which ones you prefer. And the publish does not create any subscriptions on its own. So if you do just the publish and start sending your stream, this essentially ends up nowhere. It's like a black hole, it doesn't get forward anyway, until you add subscriptions elsewhere. And I'm sure you've seen this coming. This is what a typical conferencing setup looks like. You have a few call parties, each one publishes their stream. These are send-only streams. And without subscription, those aren't going anywhere. So we can add subscriptions now. You have one of them wants to listen to Kermit, so we add a subscription there, and then the stream is duplicated there. And then you can add more subscriptions. Now everybody wants to listen to Kermit. And then to end up with a full-on conferencing scenario, you add more subscriptions, and eventually everybody is subscribed to everybody else, and everybody receives everybody else. And this is a fully fledged SFU, basically. If you're familiar with Janus, this might look very familiar to you, especially the video room plugin. And in fact, and I want to be careful when saying this, this is so similar that, and because we're able to talk WebSocket and JSON anyway, we put a kind of a translation layer into place where RTPengine pretends to be Janus. I don't want to say it's fully compatible because it's really not. It just implements one very specific subset of the Janus API. And depending on how you use Janus, if you're lucky, if you do it right, it may be possible to just switch the two out and then use this instead of Janus. Just for one specific use case, just for the video room plugin. To wrap things up, for the SFU, all STP manipulations are supported. You can do this for WebRTC, you can do this for plain zip, you can do transcoding. You still have full support for the kernel module, including mix and match SRTP encryption, decryption. And you can also mix this with calls set up through offer answer. So this is what you would use for Siprec, for example. And then I had some examples here, but I see we're out of time. So I'll just say thank you. I think if the slides are made available, you can look at the examples afterwards. Thank you for listening. Any questions? Some questions?
We have a mic coming up from the back.
So I had some hardware SBCs that we don't use anymore because we replaced it with OpenSIPs. But they came with some hot knife cards. And as far as I can tell, I have no use for them whatsoever, and they're garbage. Do you think hot knife cards, these PCI Express hot knife cards, are worth anything? Or should I just put them in the recycling?
I would love to answer that, but I don't know what that is. Sorry.
What about the scalability? How is it scalable? How it works?
So in terms of raw performance, I started talking about doing hundreds of calls on one machine with existing solutions 10 years ago. With the kernel module, this goes into the thousands, so there's an improvement of at least tenfold. The highest number I've seen was somebody running 15,000 calls, concurrent calls on one machine only. To scale it out sideways, you can use, if you use Kamailio or OpenSIPs, there's a load balancing logic in there where you can have multiple RTPengine instances running on different machines, and the module will then do it round robin or in any kind of way, just spread out the calls. Okay. One over there.
Thank you. Two questions. Will the RTPengine support Silk codec soon?
Silk, I don't think we have Silk as such. We have it as part of Opus because that's kind of Silk.
Okay.
We don't have, I'm not sure actually. I've never seen Silk used anywhere, to be honest.
It's a lot.
Yeah. Even though now that you mention it, I think it is supported actually, but I'm not sure.
Okay.
I can check. If you come back to me, I'll look it up.
Yeah, the second question is, for example, if basic code A code B, right, they are using the IPv4, but once I switch to a V6, so if we don't delete the previous V4 connection, what happened in RTPengine?
So RTPengine is able to bridge different networks, V4 and V6. Even different IP addresses, multiple IP addresses. You just need to set up RTPengine to actually use a V4 address and a V6 address on one host. And then you need, as part of the signaling, you need to tell RTPengine which way a call is going. So if it's coming from V4, obviously it will see that. But if you know it's going to a V6 address, you need to tell RTPengine to use V6 for the outgoing offer, and it will handle the rest automatically. What do you mean the previous V4? You mean like as part of a re-invite? So we have recently added the capability to close sockets, to close ports during the runtime of a call. So previously all ports would stay open until the very end of the call. We are now closing them as needed. For this particular case I would have to check, but it's certainly possible that if that happens in a re-invite, that the old ports would be closed and then they could be reused. Yeah, okay. Anybody else?
Great. Let's have a
Nope.
round of
All right.
applause for Richard. Thank you very much.